So ways that we can make alcohols, other than the alkene reactions, we're going to look at reduction reactions. So this is from chapter 13. The first one involves an aldehyde or a ketone. So if there's an H there, that's the aldehyde. For an R group, that's the ketone. Last semester, we used H2 platinum to reduce alkenes and alkynes. And guess what? We can also use them to reduce alcohols. So we'll get the two H's added there. So this is for aldehyde or ketone. All right, questions on that reaction? So I added here that this can also reduce the alkenes and the alkynes. So that's something to be aware of if you're doing a synthesis and you have alcohols as well as alkenes or alkynes in your molecule. If you only want to reduce the aldehyde, you don't want to use H2 platinum. Something that you could use is the next reagent here, which again can be used with aldehydes or ketones, is sodium borohydride. This reaction is often done in alcohol. And this will also reduce your alcohol. And that works for a ketone or aldehyde. This one will not do anything to alkenes or alkynes. So if you're having that molecule that has those two functional groups, an alkene and an aldehyde, sodium borohydride will reduce only the aldehyde, not the alkene. If you have a carboxylic acid or an ester, so the H there can be the H for carboxylic acid or ester. We would use excess lithium aluminum hydride, followed by water. That will reduce to the alcohol. So it will go all the way to the primary alcohol. And your side product, if you wanted to keep track, would be another alcohol. You'd either get water or an alcohol if you had an ester there. So this lithium aluminum hydride can be abbreviated as LAH. This one also works on aldehydes and ketones. So there's three ways to reduce it. The H2 platinum will do the aldehyde ketone, but it also does the alkenes, alkynes. Sodium borohydride is mild. That will do aldehydes and ketones. If you want to reduce a carboxylic acid or an ester, you have to use a stronger lithium aluminum hydride reagent, which can also do the carbonyl or the aldehyde ketone. So that's something to be careful of if you have most of those things in your reaction. And in a couple of chapters, we'll look at ways where you can specify or protect these so that they don't get reduced if you're trying to reduce to one of the bigger functional groups here. All right, questions there? Anybody still writing? Okay, so this is 13. We're going to start with our aldehyde or ketone. A Grignard reagent is one that has an R with a magnesium bromide next to it. You could also use a magnesium chloride, so it's some magnesium halogen. These are made by taking an alkyl halide, so if you had an R prime Br or ethyl bromide or something like that, and you stir it in ether with magnesium metal turnings, and that will insert the magnesium into here. So if it was just R prime Br, this R is going to be electrophilic, but we add that magnesium in there and it switches it, or does an umpalung and switches the polarity. So that R now is negative, which can attack this electrophilic carbonyl. And when it does that, that O stays there. My H or R stays here as well. But I form a new bond to this carbonyl carbon. There's my R prime. And in the process, in that second step with water, I pick up a proton there to make the alcohol. So this is a Grignard reaction. So this kind of falls into the two categories. It can be a reducing reagent. You can kind of think of it because it does go from double bond to H. So we're adding hydrogens here, but mostly we're adding a new carbon bond. So the Grignard reagent is going to add a new carbon bond. If you do this reaction with an ester, we need to use excess of the Grignard reagent. And we're going to add our groups 2 times. So one R prime will get added, and then the second one will as well. And our side product is the OR that gets kicked off from the ester part, which will get protonated there. So that makes an alcohol. So this is also a Grignard. And with this one, we're going to get a tertiary alcohol. So reaction of a Grignard with an ester will always give us a tertiary alcohol. All right, any questions there while you're still jotting things down? Does anybody need some more time to write? So first I have an alcohol. This is the reaction that we first just did. Be TMS chloride. And for this one, you can use primary alcohols, secondary, and tertiary. So you can protect any of those groups. This is a protecting group. And that's trimethylsilane. And the next one is just T-bath to a way to take off the group. A lot of times these products, the alcohols will be a liquid or an oil. But once you take or put the TMS group on there, it gets turns into a weird foam. And then if you take the group off with the T-bath, then that will just give you your alcohol back. And then your product is back to an alcohol and an oil. All right, the next one here, we have an alcohol. If we use zinc chloride, that will convert the alcohol into a chloride. And this results in an inversion of stereochemistry. This is done via an SN2 reaction. We can do the same thing also with SOCl2. That will also invert stereochemistry. And you'll see this one in lab whenever you end up doing your experiment. We'll do a halogenation of alcohol. That's an SN2 reaction as well. And if for some reason you really wanted to use a bromine instead of a chlorine, we would use phosphorus tribromide. Which is also an inversion via an SN2 reaction. Questions on any of those reagents? So in the last semester, if we had alcohol that was a bad leaving group, you needed to tosylate it in order to make it a better one. Now we can use chlorine, or actually this last one should be bromine. Right, so that should be PBr. PBr3 is going to put a bromine in place of that. So we can switch it to a halogen, and in the process, this will also change the stereochemistry. When we tosylated the alcohol previously, that maintained the stereochemistry, but with any of these reagents, we can switch it. So if your product needed to invert the stereochemistry, that is a good option here. Questions on any of those reactions? All right, so let's look at a couple of problems here. And we have quite a few actually to add to this page. The first one is a primary alcohol. We're going to add to it sodium dichromate with water and sulfuric acid. These are oxidizing reactions, so we're going to be losing hydrogen and also gaining oxygens. So that alcohol is going to lose hydrogens, and it will get converted to carboxylic acid. This is the Jones reagent. So primary alcohol is going to get oxidized first to the aldehyde, and then it will keep going to the carboxylic acid with sodium dichromate. We can do the same reaction using potassium permanganate. we'll get the same carboxylic acid. That one is not named after anybody. Right, I'm going to add, yep, that's fine. Okay, so the next one is an aldehyde. With the Jones reagent. I'm also going to put CAMNO4 in parentheses here, because you can use either of those. If you have the aldehyde, that will get oxidized to the carboxylic acid. So the aldehyde is the pit stop between alcohol. It stops at aldehyde, and then it keeps going to the carboxylic acid. If you had a secondary alcohol and used either of those reagents, you would get the ketone. And this one would stop at the ketone because there's no more hydrogens to get oxidized here. If you had a primary alcohol or secondary, use PCC, which is pyridinium chlorochromate. This is the milder reagent. And it will stop at the aldehyde if you have it. Or ketone. So if you have a primary alcohol, it will go to the aldehyde. If you start with the secondary alcohol, it will stop at the ketone as well. So PCC is one of those. It has that same chromium like the Jones reagent, but it stops adding that pyridinium there, makes it milder. And then we have two other reagents that we can use to stop at the aldehyde as well. So our starting materials are all the same here. One is called DMP, which is the Des-Martin pyridinane. It's an iodo complex, which you don't need to know the structure of. So that one will stop at the aldehyde, as does the SWERN. So if you feel compelled to become a famous chemist, you can come up with a reagent and then name it after yourself. This one sometimes is written COCl2. And that happens with DMSO as a solvent. This is DMSO, which looks like acetone, except that it has a sulfur instead of a carbon double bond. All right, so there's lots of different ways to oxidize your alcohols. All right, questions there, or is anybody still writing? And this is in 14. So if I have an alcohol, this is a way to make an ether. We add another alcohol with catalytic acid. I'm going to make the ether here. This is not the best way to make an ether just because you could get a mixture of products. So if you were making just ethyl ether with ethanol, which is how ethyl ether is made in the industry, then that would work fine. But if you were using propanol plus ethanol and trying to get a methyl propyl ether, then you would have some things that are methyl ethers on both sides where it's methyl, and some where it's propyl on one side and methyl on the other. But it would be really hard to control that reaction. One of the more popular ways to make an ether is using the Williamson ether synthesis, which is one that you'll be doing in lab. In this synthesis, you take the alcohol. The sodium hydride is your base, which will deprotonate the alcohol, which can then do an SN2 attack on the alkyl halide and then form the R group over there. So that's the Williamson ether synthesis. Because it's SN2-like, you want to make sure that whatever alkyl halide you're attacking is primary or secondary. All right, another way to make an ether is one that we've seen already, which uses an alkene. This is the mercuric acetate. And instead of water, we use an alcohol. And that is the Markovnikov product there. And then once we've made an ether, we can do a couple of reactions. Ethers are actually not that exciting once you have them. They're pretty not very reactive, the ethers themselves, which is why we use it as a solvent, which you guys see frequently in lab. We use ether a lot for a solvent. So if you add a halogen or a HX to an ether, the OR prime is going to get protonated. And then once that's protonated, it makes it a good leaving group. And then the X minus can attack at the R group to make the RX and then kick this OR prime off and actually leave as the alcohol. And that reaction can happen again. So you can get protonation of the OR prime. When it's just the OR prime, the X minus can come in and do that attack there. And this product assumes that R and R prime are primary and secondary. So if R prime was on a double bond, or if it was on a benzene ring, you would only see the RX, and then it would be the benzene ring with X on there. And we should see a couple of examples of those today. So that's ethers. And then now we're going to look at reactions to make epoxides. The most popular way is to do it using an alkene with MCPBA, which is the same as an RCO3H. And we saw this last, I guess that would have been last semester, when we use this with water. So we use this to make an anti-diol. But now if you don't add the water step after that, you end up with an epoxide, which is that three-membered cyclic ring. MCPBA is metachloroperbenzoic acid. You can also make an epoxide using the Williamson ether synthesis. If you have an OH and a Br in the same molecule, you add a base to that. In this case, it's sodium hydroxide. So the mechanism is the same, where the sodium hydroxide will deprotonate that alcohol. And then that alcohol is going to do an SN2 attack at this carbon here on the backside of the Br, and then we form this new bond here. So this is an intramolecular SN2. And the OH and the Br have to be on opposite sides, or trans. And then once you have formed the epoxide, you would add a nucleophile followed by water. So if I have an N or a nucleophile that is negatively charged, this one is SN2-like. My nucleophile is going to attack on the less substituted side, so the alcohol ends up on the more substituted side. And then that alcohol gets protonated. So here the nucleophile can be a negative OR, OH, SH, SR. You can attack it with a Grignard, or H-, which would be lithium aluminum hydride or sodium borohydride. We can also use a CN or CN- to attack that, but I'm going to put that on the carbon bond forming page. All right, questions on that one? All right, so I am to the bottom of my page, so I have to flip over for the next couple of reactions. Hopefully you're finished writing that one. All right, so this is still 14, just so I know where that is. This is an epoxide opening under acidic conditions. So we have a little bit of acid there. This one is SN1-like. So my oxygen from the epoxide goes to the less substituted side, and the OR can add over there. So that can be whatever neutral nucleophile as well. All right, and then these reactions are from the second half of 14. These deal with thiols. If you add Br2 plus sodium hydroxide and water, this will make a disulfide. So the Br2 and the sodium hydroxide will do a couple of different things, and it ends up being an S-, which can attack another molecule of itself. So this is a disulfide. If you have an RS-, and an R prime with a halogen, that will just do an SN2. This is a sulfide thioether. And then one more here. If you have that sulfide thioether, you can react it with an R prime X. And it will alkylate it. So that R prime will get added here. And that happens often in biological systems with any sulfur amino acids. All right, next we're going to go to the carbon-carbon bond forming page just to add those reactions with the epoxides, and then we'll finish up with the oxidation page. So if I add CN-, that is considered negative because it has a negative charge here, or under basic conditions. That's going to add to the less substituted side. If you wanted to add that same CN, but to the other side, you would just use HCN. Get that? So all we've done there is now this HCN, because there's a covalent bond there, that would be considered a neutral nucleophile. All right, and then we said we could use this with Grignards. I put this on this page because that is a carbon bond forming reaction. And that will attack at the less substituted side because the O there, or the R group, is negative. All right, questions on any of those? The last couple of reactions are on the oxidation page. There's just 2 that we have to add there. So this is on page 17. With that thioether, if we add sodium periodate, that is going to oxidize this to the sulfoxide. So it looks like sulfur. Actually, it looks like a carbonyl, but with the sulfur there. So this is a sulfoxide. So this is oxidation. We're not losing hydrogens, but we are gaining oxygens. So oxidation is loss of hydrogens and also gain of oxygen. And that is a milder oxidizing reagent, that sodium iodate. If we use hydrogen peroxide, that's going to add 2 oxygens. And sulfur is one of those things that can take on 10 electrons. So we get this sulfone. So those are our different sulfur groups. We have the thiol, which is the SH. Then there's the sulfoxide, which has the, looks like a carbonyl, but with an S. And then the sulfone has the 2 oxygens there. And then there's also the disulfide. Oops. All right, was anybody still writing? Hopefully not. Okay, so the first reaction is chapter 17. We have the diene, the conjugated diene. And I'm going to number these 1, 2, 3, 4. If we add HX at 0 degrees, we'll get H adding to the end, because H is going to go to the carbon with more H's, and then the Br goes to where the carbocation is. This is the 1,2 addition. And here, oops, I put Br there, but X can equal Br or Cl. This should really be X here. And if you do this reaction at warmer temperatures, 40 degrees Celsius, the H goes to the end like normal. And then in the process, the alkene moves to here from the resonance structure. And then our X from the HX adds to the end. This is the 1,4 addition. If you add X2, so Br2 or Cl2, we would get the same pattern here. So at cold conditions, we'll get Brs here. Or those Brs can be X's. So put X over the arrow. And then for the warm conditions, we'll see the same thing. Questions on reactions there? All right. So I start with a diene. I'm going to put an R group on there just so I have an electron donating group because that helps the reaction. And then here's my dienophile with an electron withdrawing group. You don't have to add extra reagents. We just warm it up a little bit. And you'll be doing one of these in lab as well. So I have electrons going there to form a new bond. Electrons going to form the pi bond there, and then these ones will form a new sigma bond. So there's the new bond that was formed. This is a new bond. This is a new bond. So we make cyclohexene. And then EWG is an electron withdrawing group. So this can be an aldehyde, carboxylic acid, ester, a CN. It can also be a halogen. All right, any questions on that reaction? So that's just the one that we have to add. There'll be an extra one tomorrow for 17C, but that's the general Diels-Alder reaction. All right, anybody still writing on that one? So this one is under our Diels-Alder reaction. Which we can write over here as Diels-Alder. That one's from C, in case you want to go back to that. So if we add heat to this reaction, one of these pi bonds is going to form a new sigma bond. This pi bond is going to form a new pi bond here. And we're going to break a pi bond, or I'm sorry, a sigma bond to form a new pi bond. So I have a new sigma bond right there, a new pi bond, and a new pi bond. Questions there? I think I actually do have this backwards. This is the cope. Cope is with carbons. Clizen is with the oxygen. I had that backwards, I apologize. So this next one is the Clizen. The arrow movement is the same. So we're going to take one of these double bonds to form a new sigma bond. One of these pi bonds goes to form a new pi bond. And we break the sigma bond to form a new pi bond. So we now have carbon double bond oxygen, a new sigma bond, and a new pi bond there. And that one is the Claisen. All right, any questions there? All right, so the cope is the one with the carbons, and then the Claisen is the one with the oxygen, which I should remember, you would think, since I did a whole seminar in my second year of grad school on the Claisen reaction. But apparently, out of sight, out of mind. All right, anybody still writing there? Okay. And this might be out of order from what we did in the lecture notes. But I'm going to start with a benzene that has 2 electron donating groups on it. We add sodium metal with methanol and ammonia. And this is the Birch reduction. So we start with benzene. And we're going to end up with cyclohexadiene. And this is the Birch reduction. So your electron donating groups can be R, which is going to be any carbon group where it's methyl, ethyl, isopropyl, something like that. You can have an OH there, an OR, NH2, or an NRH. So these are groups that have inductive abilities to donate electrons into the ring, or they have electron lone pairs that they can donate into the ring. So that is the Birch reduction with electron donating groups. We should also add the Birch reduction with electron withdrawing groups. But the other thing to notice here is that the double bonds are on the carbon with the electron donating group. And that's going to be the opposite for the electron withdrawing groups. So the same reagent. And now the double bonds, you're still getting cyclohexadiene, but the double bonds do not want to be where the electron withdrawing groups are. And the electron withdrawing groups are things that like aldehydes. So a carbon double bond oxygen, a ketone, a nitrile, a sulfoxide. If you have an N double bonded to something, carboxylic acid, or an ester. So the electron withdrawing groups do not want to try and stabilize those double bonds, so they want them away from them if possible. All right, questions there. And then we have reactions to add to the oxidation page. Sorry, that should be chapter 18 that we just added, not 14. This is 18. And this is with the Jones reagent. So before we use the Jones reagent, in order to oxidize a primary alcohol to a carboxylic acid, or you could use it to oxidize a secondary alcohol to the ketone. But if you have a benzene or a benzylic proton present, that is going to oxidize that to the benzoic acid or the carboxylic acid. So for this one, you need a benzylic hydrogen. So in order to do that reaction, you need a benzylic hydrogen. If you were doing this reaction with ethyl benzene and sodium dichromate with all the bells and whistles here, you would still get benzoic acid. So it's going to cut everything off. Or if you had if R was a 50 carbon long alkyl chain, you'll still get benzoic acid. So as long as there's a hydrogen here, that's going to oxidize here. And this tert butyl group does not get oxidized because there's no hydrogens on that carbon. All right, and then the next reaction is the same thing, but with KMNO4. So KMNO4 and the sodium dichromate have very similar properties. All right, and then I forgot about one to add to our functional group transformation page, because there's just the one. This one we've actually already seen in some form. And that is with NBS, which is N-bromosuccinimide. And that will place a bromine on the benzylic carbon. And this one also you need a benzylic hydrogen. And then that NBS is N-bromosuccinimide, in case you forgot. So previously, I think that might have been in chapter 11. So in last semester's stuff, we used NBS in order to brominate at the allylic position. So the carbon next to the double bond. This is doing the same thing, except it's on the benzene. So we can brominate right there. So if you have ethylbenzene or propylbenzene, this is a way to add an extra functional group that we can use as a functional group handle there. All right, questions on any of those? So to reduce benzene, you have 100 atmospheres with high temperatures. That will give you cyclohexane. So H2 platinum doesn't work regular on benzene. You have to use high pressure and then high heat. So some students on their total synthesis project use this method in order to reduce to their structure. So if you notice on the syllabus, your last you have 8 virtual labs, and then you're working on a total synthesis project where I assign you a larger molecule, and then you'll be putting together a synthesis for that large molecule. Okay, any questions on that reduction? And in the first one, we have just benzene. And you're going to add a halogen with a metal catalyst. So it will be iron with an X3 or aluminum X3. It's just a little bit sloppy there, sorry. So if we had an alkene with Br2, that would add 2 Brs across the double bond. But for benzene, that's more stable, so we have to do this reaction in the presence of a halogen, or I'm sorry, this catalyst here, the iron or aluminum catalyst, and that's only going to add 1 halogen to the ring. So X here equals Br or Cl. All right, so that's a way to put a Br on a ring. And that's directly on a ring. So there's just benzene, and then we add a halogen there. If you want to add a sulfate group, you use fuming H2SO4. And that's concentrated. So concentrated sulfuric acid. And that adds the SO3H group there. If you already have that SO3H group on there, and then you add dilute H2SO4, that will remove the SO3H group. So we put an H there. So this is removing blocking group. And we'll talk more about that later. So the SO3H group can be used as a blocking group. If you needed to make aniline, you could first, or if you wanted to put an NO nitro group on there, you add HNO3 or nitric acid in the presence of H2SO4. And that will add the NO2 group. Okay, so the sulfuric acid, you might sometimes need an SO3H group, but often if we're putting that on a ring, it is to use it as a blocking group. The halogens, if you needed to use a Grignard on a benzene, that's how you could make that. So benzene, add a X there if you wanted to add Br, and then insert the magnesium to make this attack something else. And the nitro group, adding that is handy because we can reduce that later to make an amine. All right, any questions on those reactions, or is anybody still writing? The next page we'll add to is the carbon-carbon bond forming page, which is 13 on my book. So we're going to start with the Friedel-Crafts reaction. And this is a way to add an alkyl group. Oops. All right, so that alkyl group should be orange there. And we'll add that R prime. This is the Friedel-Crafts alkylation. And with this reaction, there's a couple of caveats here, or these asterisks. It can, rearrangement is possible here. So if you wanted to add a 5-carbon chain, you would not be able to use chloropentane because it could rearrange. The alkyl halide, let's see, polyalkylation must be sp3. So you would not be able to add a CH2 carbon double bond with the chlorine on there. So it has to be sp3. And then sometimes you can get polyalkylation. So that means that it could add more than one time. That would be a practical if you were in the lab trying to do this reaction. But for class, I'm not going to mark you down or anything if you don't have the polyalkylation product. So you don't have to worry about that on your quiz or exam. If you want to avoid a rearrangement, what you can do is do the Friedel-Crafts acylation. And that is just using an R group with a carbonyl next to it. Same AlCl3. So you would have this carbonyl after you added that on. So if you wanted to add pentanal, or with the chlorine on the end, so it has that ketone there, or that carbonyl, and then we can reduce that down to the H's later. So this is the Friedel-Crafts also. There's no rearrangements. And no polyalkylation. There is one caveat, or an asterisk here, a giant one, for Friedel-Crafts. This is both of them. These will not work if you have a strong electron withdrawing group or strong electron donating group. So if you had a sulfonyl group on there, so for electron withdrawing, it might be SO3H, NO2, or carbonyl. And then for electron donating groups, these would be an OH or an NH2. If you have any of these groups on the ring already, on the benzene ring, you cannot do a Friedel-Crafts reaction. So with these reactions, it's kind of like with our alkynes, or if you're doing synthesis, you want to make your carbon-carbon bonds first. If you have a halogen on the ring, then you can do the Friedel-Crafts reaction, but not with a nitro group or anything like that. Okay, questions there? All right, and then the last reaction page for today is on the reduction page. And that is page 19. And these are with groups that are already on the ring. So if you had that nitro group on the ring, you add zinc in the presence of HCl. That will reduce the nitro group to the amine. So that is a way to make aniline if you needed to synthesize that. And then if you did a Friedel-Crafts acylation and you needed to make that into the alkane, we would use zinc amalgam. So that's in the presence of mercury metal with HCl. We heat that, and you get the alkane. This is called the Clemmensen reduction. So if you wanted to add that 5-carbon chain, we would do the Friedel-Crafts acylation first and then reduce your carbonyl to the alkane. And that would be a way to get around the rearrangements. All right, any questions on any of those reactions that we added? So there'll be a couple more that we add tomorrow. There's actually not a ton of reactions for this chapter, as we've seen in some other chapters, but it's the order in which you add things that really makes an impact on the synthesis. Anybody still writing? And this is a reaction for if you have a bromine present. So the bromine is needed. And you also need an electron withdrawing group, either ortho or para to that bromine. And then you add to that sodium hydroxide. And that's heated at 70 degrees. And you follow that with some acid, and that will make phenol out of that Br. If those electron withdrawing groups are not present, you won't be able to do that reaction at 70 degrees. You would have to heat that one up, I think, to 100 or 350 degrees, I think Celsius was what it was, so pretty hot. So for this one, you need that electron withdrawing group on the ortho or para position. They don't have to be on both. All right, and then on page 9, keep that up here. If you have chlorobenzene, we add NaNH2. So we used that NaNH2 before in a lot of reactions with alkynes, either to form the alkyne or to do a reaction with it. So we know it's pretty nucleophilic. And if you add that sodium amide to chlorobenzene, that will actually make aniline. So if you had a chlorine on your benzene ring and you wanted to swap that out with an amine, you can do it doing that reaction. So this would be instead of going through the nitro group. But you could also go through the nitro group to get that amine. It'll just depend on whatever else you had on the ring. And then we have a reaction of toluene. This is a reaction we've seen already, just not in excess. So if you add N-bromosuccinimide in excess, we make 3 Br groups on that benzoic carbon. You might see that sometimes written as CBr3. So this would be a way, if you had the CH3 here, which is an ortho-para director, to swap it out to a meta director. So adding all of these bromines on here makes this group electron withdrawing, which would direct the next group meta. All right, questions on any of these reactions that we have? Those are the only 3 that we need to add today. And I'm on functional group transformation page, page number 9. And a lot of the reactions that we did in chapter 20, we also saw in chapter 13 with the alcohols, those like the reduction of carbonyls. So I'm not going to re-add those to the book because they're already in there, but just be aware that some of these reactions may be in chapter 13. So this is from 20. First we have an aldehyde or ketone. We're going to add an alcohol to that. in the presence of catalytic acid. And what you can think of is this oxygen here of the carbonyl. You can draw a line down there and kind of fork split it open. And then you're going to add an OR double prime from the alcohol to each side of that. This is an acetal. And this is used as a protecting group. You can only use acetals on aldehydes and ketones. So this will not work on a carboxylic acid or an ester. To remove the S or acetal, you just add water and catalytic acid. And that will reform the carbonyl. And you'll be able to see that product in your lab if you haven't done it already. Questions on either of those two reactions. So that acetal is used as a protecting group. So if you needed to do a reaction with where you're only reacting with an ester as opposed to the carbonyl, then you can protect that carbonyl. And we'll see a couple of examples of those today. If you add an amine, a primary amine, to a ketone or aldehyde, you're going to form an imine. And what's going to happen is the nitrogen is going to take the place of the oxygen. And then the R group comes along, as does, nope, just the R group comes along. There's nothing there. Just it should be N double bond to carbon and then the R prime. So those hydrogens will get picked up in proton transfers. So a primary amine plus a carbonyl gives you an imine. If you do the same reaction with a secondary amine, so there's two of these R groups. The N will still take the place of the oxygen. Both R's come along, and then we're going to form an enamine. The ene for the double bond, and the amine for the nitrogen. So secondary amine plus carbonyl gives you an enamine. All right, questions on that one? If you wanted to employ a different protecting group rather than the acetals, we can make a thioacetal. Oops. So the sulfurs will act just like the oxygen, and we form the thioacetal. These are nicer to use if you're working on a different part of your molecule and there is acid and water present. With the regular acetals, if you do that reaction in the presence of acid and water, you will deprotect your carbonyl, but these thioacetals require different reagents in order to remove them. Or they're a little bit sturdier. This also requires water and acid to remove it, but they're not as labile as the other ones. Questions on that. And then when we get to a later reaction page, we'll see there's a way to reduce this so that we just get the alkane back. All right, another reaction that we're going to add to this page is not exactly carbonyl related, but it is a way to convert an alkyl halide into an ylide using triphenylphosphine, followed by N-butyllithium, which is a base that has 4 carbons, which is the butyl. N means it's a straight chain carbon. And then the last carbon that's is ionically bonded to lithium. So there's a C minus and then the Li plus. And when you add triphenylphosphine, that's going to substitute and replace the halogen, and the base is going to make our carbon negative. So we'll have the negative carbon here and the positive here. And you may also see it drawn as our double bond PPH3. And this is called an ylide, which is used in the Wittig reaction. And we'll see that carbon-carbon bond forming reaction in a second here. Did you finish sewing?
Nope.
Or cutting out Beer's twin?
I'm done cutting out the string.
Oh, you need to tie a knot?
But not the twin. Because I might like it. Because today Beer's getting a little sibling. Baby Beer. No, little baby Beer. Yeah. Little Beer is going to look more baby.
Alright, so this is the carbon-carbon bond forming page, which is page 14. I'm going to add potassium nitrile, and that's going to form a cyanohydrin. So that Cn minus is going to attack the carbonyl, so you add that carbon or that nitrile group. This is a cyanohydrin. So that is a way to add a carbon, and when we get to the reduction page we can see how to reduce that to an amine or to make it into the carboxylic acid. Alright, the next reaction on this page is the ylide. So we add the R double prime, and then there's a C that is double bonded to the Wittig reagent. And that C can be written as a C minus and the positive P. It's the same representation. And what you end up doing is replacing that oxygen with the C to the R prime. This is the Wittig reaction. All right, questions on either of those two? So 2 new ways to form carbon. The first one also adds a nitrogen, and the second one is a quick way of adding an alkene. Previously, otherwise, if you wanted to add a carbon with a double bond, you might have gone through an alkyne and then had to do a whole bunch of other manipulations. But now if we have that carbonyl there, we can just add a carbon-carbon bond directly. So we don't have to add something with the Br and then eliminate it. All right, the next reactions will be on the oxidation page. This is page 18 in my book. So this is that cyanohydrin that you just made up here with the potassium nitrile. If you add this reaction under heated conditions with acid and water, so a lot of times you'll see H3O plus written as acid or for acid and water. What this is going to do is it's going to oxidize that nitrile, the CN, to the carboxylic acid. So I have this C to the O carbonyl to the OH. So it's going to make this nitrile right here into the carboxylic acid. All right, any questions on that one? So if you needed to add a carboxylic acid, you could do it that way pretty quickly. All right, the other reaction here involves a ketone. We use MCPBA. Or an RCO3H. And that is going to add an oxygen in between the carbonyl and an carbon. So if you think of, there's some Price is Right game where you squeeze a number in between two things, this is what that oxygen is doing. And so you have the choice of inserting your oxygen between this carbonyl and the R prime, or this position over here. And this is the Baeyer-Villiger reaction. And the order in which things shift is, if there's an H, that will shift first, followed by a tertiary position. Secondary is tied with phenyl. Primary, and then a CH3. So at this position right here, this is a tertiary carbon, and let's say this is a secondary one. The tertiary one is more likely to have that oxygen inserted into it, which is right here, versus the secondary. Questions there? And last is the reduction page. That's page 19. In this one we have an imine, we add NH2, NH2. H plus, followed by potassium hydroxide. And that is going to get rid of that imine. So we just are left with hydrogens here. This is the Wolff-Kishner reduction. And then with that thioacetal that we made earlier, we add something called rainy nickel. And that also gets rid of the thioacetal. So we're just left here with H's. So we can use those carbonyls to do our reactions and then leave no trace behind. So it's just the alkane there. Questions on either of those two reactions? All right, we have one more to add. And I'm going to have to flip the page over for this one. And this is with that cyanohydrin that you made with carbonyl and HCN and KCN. If you add lithium aluminum hydride, which is the super powerful reducing reagent, that will reduce the nitrile to an amine. All right, questions on those reactions? And the first one is just very generic. If you have a carboxylic acid, and we add one equivalent of a nucleophile, we can add the nucleophile. Actually, this should be Lg here. So that should be leaving group, where leaving group equals X minus OR minus, or this acetate group. So if you have a carboxylic acid derivative where there's a leaving group there, and we add a nucleophile, we can replace the nucleophile or the leaving group with a nucleophile. All right, any questions there? If we have a nitrile, which is a carboxylic acid derivative and a way to make a carboxylic acid, we add water in the presence of acid and heat. We're going to get a carboxylic acid. And we'll see shortly that most of these carboxylic acid derivatives, when we add acid and water to them, we get a carboxylic acid back. Okay, so here, carboxylic acid with thionyl chloride. We'll convert this to the acid chloride. And so anytime you want to do a reaction with a carboxylic acid, the carboxylic acid is not a very good electrophile, but if we add SOCl2 or thionyl chloride to make it this one, this is going to make it much more reactive. And then once you have the acid chloride, we can add water to that. Which will convert it back to the carboxylic acid. You might see some of that in your lab this week. You can react an acid chloride with an alcohol to make the ester. All right, questions on any of those reactions? All right, and then I need to flip my page over, so hopefully everybody's done writing here. Okay, so we did the ester. Next, we can use an acid chloride to make an amide. So we have an excess of a primary amine, but this can be primary or secondary amine. So if you have a secondary amine, both of those R prime groups would get added there. And then if you add an acetate or some sort of carboxylate, that will make the anhydride. Questions on any of those? All right, next is the carbon-carbon bond forming reaction page. The first one is with a Grignard, or we start with an alkyl halide. We add magnesium to make it a Grignard. We follow it with CO2 and then an acid workup. So the magnesium will insert between the R and the Br, which will make the R nucleophilic, and that can attack the carbon dioxide, which will make CO2 minus, which can get protonated with the acid that's added there. So this is a way to form a new carbon bond and make a carboxylic acid at the same time. And then now if you have an acid chloride and you add a Grignard to it in excess, this will work the same way as adding a Grignard to an ester. So we'll get the alcohol and addition of 2 R prime groups. So if you only wanted to add 1 R group with the Grignard, you'd have to use an aldehyde or a ketone to get the addition of just 1 R group. If you wanted to add 1 R group to an acid chloride and then keep the ketone without having to reoxidize it, you can start with the acid chloride. And then we're going to use a copper lithium reagent, which works similarly, except only 1 group gets added. So even though there's 2 R groups on the copper lithium, only 1 of those is going to get added, and the carbonyls can stay intact. So if you did this reaction or a Grignard with an aldehyde or a ketone, you'd end up with the alcohol, and then you'd have to oxidize it with PCC. But with this reagent, you can just add the 1 equivalent, 1 of the R groups gets added, and you get the carbonyl here. This is the Gilman reaction. So 1 R group gets added. Questions there? All right, if we have the acid anhydride, with excess Grignard, we'll get that same addition twice. And if you could start seeing the pattern here, whatever nucleophile is adding is getting added there. So this one is the leaving group, and then we're adding the nucleophile twice because there's still a leaving group there. If we do the same reaction with the anhydride as with the Gilman, we'll just add 1 of those R groups and get the ketone. Any questions on that? So using the Gilman reaction can save us a step of doing that extra oxidation. All right, we can also reduce these acid chloride or these chloride derivatives, carboxylic acid derivatives, sorry. So this is on the reduction sheet, which is page 20 in my book. And the first one is reducing the acid chloride with excess lithium aluminum hydride. So lithium aluminum hydride really reduces just about anything. And that will go all the way to the alcohol. Before, if we wanted to make an aldehyde, we'd have to reduce all the way to the alcohol and then oxidize it with PCC. But now we have a reagent that can reduce this to the aldehyde directly. This is lithium aluminum OR prime 3H. Followed by water, where R prime equals a tert butyl group. This will go to the aldehyde. So this reagent is kind of like a reverse PCC, where it stops at the aldehyde via reduction instead of oxidation. So that will come in handy. So the acid anhydride will behave like the acid chloride. but I'll put them on here anyways. So if you use excess lithium aluminum hydride, we're going to get the alcohol. And if you use that same LiAlOR3 reagent, that will get you the aldehyde. And for an ester, we can reduce that also. With lithium aluminum hydride. I'm just going to abbreviate it that LAH here. That will go to the alcohol. And then there's also a reagent that will reduce the ester to the aldehyde. This one is abbreviated dibal H. Oops. And this will give us the aldehyde. And the structure of dibal H has an aluminum with one hydride, and there's two diisobutyl groups. So that's diisobutyl aluminum hydride. This can also be written as dibal or diba. I've seen it both ways. So diba or dibal. And that will stop at the aldehyde. All right, questions on any of those? We have one more set of things to add, I think. Let me double check. Nope, that was it. All right, so those are all of your reactions for 21's A and B, and we can add to the part C reactions tomorrow. All right, do we have any questions on those reactions? So the pattern is similar. We'll probably run through a mechanism of one of these, and then you can see how these are, it's the same reaction occurring over and over again with these reagents here. So if you think of the H here in terms of the nucleophile, instead of something like a Grignard, then you can see the pattern is the same. All right, so let's go to our first poll question. So this will be starting with an alcohol. And over the arrow, we'll have an acid anhydride. So those are R primes. And when you add an alcohol to the acid anhydride, we're going to add this part of the acid anhydride to the alcohol. to form an ester. So that is one way to make an ester. And we use that active acid anhydride to make the ester. We can also do this reaction with an amine. The same acid anhydride. If we use acetic anhydride, with an amine or an alcohol, this is often used to kind of deactivate those groups. So this will make an ester up here with an alcohol and the acid anhydride, and then with the amine, we will form an amide. So I mentioned these two reactions can be used to deactivate. If we acetylate an alcohol from salicylic acid, that's how we make aspirin. So you were just putting this group on an aspirin alcohol. And then acetaminophen, which is also known as Tylenol, is made using a free amine with acetic anhydride as well. If you have an acid anhydride and you want to get the carboxylic acid back, just like we did with the reactions yesterday, the other acid chlorides, we just add water and that will hydrolyze that. So sometimes if you have a bottle of acetic anhydride that's been sitting around too long, or if somebody left it open, this will hydrolyze to the acetic acid and then it won't be as reactive. All right, any questions there? So the other thing I should note for this amine, this can be a primary or secondary amine. All right, if you have an ester, a carboxylic acid, and we need to make an ester, we add an alcohol in the presence of acid, and that is the Fischer esterification reaction. If you have an ester and you add to that sodium hydroxide, you'll form the carboxylate. And this is actually, so an ester, a triester is a fatty acid where there's a whole bunch of these or 3 of these esters. And when you add sodium hydroxide to that fatty acid, and that will form the carboxylate. This is how soap is made actually, if you have some sort of fat. So you've probably heard of olive oil or different olive oil soaps. So they use olive oil, add sodium hydroxide or lye to that, and then they can do the wash up and get soap out of that. So that's that carboxylate salt that is making the soap. And depending on what kind of fat you use for the soap, you'll get different types of soap. So it could be a hard soap or a soft soap. Or if you've seen Fight Club, they used fat from the liposuction banks to make luxurious soaps. So that was with lye there. All right, and then if we have an ester, we add ammonia. We'll make the amide. This is a very slow reaction. So we've seen other ways to make amides that work better. The acid chloride would work better to make the amide, as would the acid anhydride. So if you needed to make an amide, you would use one of those. Or you could use a carboxylic acid with an amine in the presence of DCC, which is dicyclohexyl amide, carbodiamide. So there's two cyclohexene rings on a nitrogen, which is double bonded to a carbon. This is a coupling reagent. So what that means is you add this into the reaction and it makes the OH a much better leaving group so that the nitrogen can come in and attack there. And that DCC is often used for making amino acids or peptides in peptide synthesis. All right, and then with the amide, if we add water and acid, we're going to get the carboxylic acid back. And another reaction with an amide, the last one we'll add today for the functional group transformation, is if you have an amide and you add SOCl2 or thionyl chloride, this reagent we've seen previously to swap an OH alcohol to a chloride or the carboxylic acid to the acid chloride. But if we add it to an amide, it's going to react as a dehydrating reagent, and it's going to remove a water. And what you get is a nitrile. So if you want to think of this oxygen plus the two H's here get lost as a water. And then we end up with the carbon, which is right here, right there. So that becomes triple bonded to the nitrile. So if there's reactions where you might need to go from an amide to a nitrile, maybe you want to add a Grignard to that, then you can use that dehydrating reagent SOCl2 in order to get the nitrile. All right, any questions on those reactions? Okay, so this is the carbon-carbon bond forming page. So page 14, we're going to continue with chapter 21 reactions. We did the cuprate. This is the one that we just made, so that nitrile. If we add a Grignard to that, followed by water and acid, we're going to get the R group added, the R prime from the Grignard, and that water will give us a ketone. So we won't even see that nitrogen in the product. If you react a nitrile with a Grignard, we end up with the ketone. This has a similar effect as adding the cuprate to an acid anhydride or the cuprate plus the acid chloride. In those cases, we get a ketone. So the nitrile here is going to get lost as ammonia, and we end up with a new carbon bond and then that carbonyl there. Questions on that reaction? And then the last two that we'll add today are on the reduction page, page 20 for me. This is a reaction with the amide. And our friend excess lithium aluminum hydride. Followed by water, is going to reduce our amide all the way to the nitrogen or the amine. So we get rid of that carbonyl. So 2 H minuses are delivered to this, and that carbonyl oxygen will get lost as water. And if you have the nitrile, we can reduce that also with lithium aluminum hydride. And if it helps to draw the hydrogens in here, you can do that. All right, any questions on any of those reactions? So I did mention that there was a lot of reactions for this chapter, but they're very similar if you start seeing that pattern there, which is page 10. And if you're using your course pack, you're beginning to notice that we're getting towards the end of the course pack, which is kind of exciting. All right, let's see. This is chapter 22. And in this reaction, I will add bromine, or Br2, in the presence of acid. So you might see it as an H3O+, or even acetic acid is sometimes used. And what you will observe is that a bromine will get added to the alpha carbon at the more substituted position. So the bromine will go to the more substituted position. So if you needed to add anything here, or you wanted a functional group to get added to this position, we would use Br2 in the presence of acid. If you have that group then, that bromine at the more substituted position, and now we add pyridine, which is a mild base, that will eliminate the bromine. So now we have an alpha beta unsaturated carbonyl. So this is the alpha position. This is the beta. And we'll learn how to use that alpha beta unsaturated carbonyl later in this chapter. So there is a way to add a Br to the alpha carbon, and then we can eliminate that if we need to. If you have a carboxylic acid with an alpha carbon, we can add a bromine to that as well with slightly different conditions. So we need Br2 with PBr3 followed by water, and that will brominate the alpha position of the carboxylic acid. This is the Hell-Volhard-Zelinsky reaction. Sometimes abbreviated HVC. All right, questions on any of those couple of reactions? All right, so we're still in the functional group transformation. I just have to start a new page here. If you want to add a bromine to the less substituted side, and this will only work if, in this current state, if you have no alpha protons on the other side, really. So Br2 under basic conditions. We'll add a Br to the less substituted side. So I would only use this method if there's no other alpha protons present. All right, so that sloppy chicken scratch says only use with no other alpha protons present. If there were other protons, you would get a very large mixture of things, which we want to avoid. All right, and then we have another compound in which there's no alpha protons. Oops. On the other side, and this is specific to a CH3 group right here. If we add sodium hydroxide with Br2 followed with acid, we get a carboxylic acid. So this is another way to make a carboxylic acid. This one only works with methyl ketones. So meaning that there is a CH3 here. So what happens is the sodium hydroxide is going to do this reaction up here, but it's going to brominate 3 times. So this is in excess. You would brominate 3 times here. And then once you follow that up with water, the CBr3 that would form here is a very good leaving group, and that will just get hydrolyzed. So that's how you get that one there. So if we had an ethyl group here, like we do above, you just get one Br that's added there. Any questions there? So next we're going to the carbon-carbon bond forming page, which is page 14. And this one begins with an aldehyde, although you can do it with the ketone as well. Add sodium hydroxide. So you get your aldehyde back. We're going to form a new bond at the alpha carbon, which is right there. So this is my new bond. And then I'm going to react it with a second molecule of the aldehyde. So this enolate that forms is going to attack this carbon right here. So we'll get an alcohol, and then everything that was there comes along. So I have a CH2 and then the R group. This is the aldol reaction. right, so again, you have the aldehyde. You react it with sodium hydroxide. That's going to form the enolate at the alpha carbon, which can then attack a second molecule, which is shown in orange here. So you're going to form this alcohol plus this R group here. If you heat that reaction, the same thing. So we have the same starting materials. And then you heat the reaction. What's going to happen is this will get kicked off. This is one of the rare times we can use OH as a leaving group because it's in the presence of OH. So this will get eliminated and we form the double bond there. So when you're drawing the products for these, if you want the shortcut, you draw the aldehyde that you started with, go to the alpha carbon, draw a double bond, and then you can think about taking a second molecule of this and shuffling it under here and removing that oxygen and drawing the R group there. So what we've done is remove the OH as a leaving group and then formed a double bond right there. This is the aldol condensation. So the condensation involves heat and the removal of water. So we remove the OH here and the H from that alpha carbon. Okay, any questions there? Okay, so, and this is just in case anybody's still writing. And then we're going to go to a couple of questions before we add some more reactions. All right, so questions here. So these are from part B. So this is just an aldehyde with no alpha protons. In the presence of sodium hydroxide, we add a second one, second aldehyde here. And the formaldehyde is the one that is getting attacked. This is our aldehyde. The new bond here is green. And then I form the OH here. So that would be the aldol reaction part. And then if you heat that reaction up, we're going to get the double bond version. So we'll have this aldehyde again. This is the new bond. And then it's just the one carbon. If you want to draw the aldehyde hydrogen here, you can. So this one has no alpha protons. We can just stir all these things in together and you'll get the aldol condensation product. If you wanted to do a reaction where this is the enolate, we would add LDA minus 78. Once that forms the enolate, then we add our aldehyde. You draw your original aldehyde. The new bond is coming off of the alpha carbon. And I've added 3 carbons here. So 1, 2, 3. This is 1, 2, 3. So this is a quick way to do an alpha beta unsaturated carbonyl. So you could have, this could have been done, I guess, also with the Wittig, but you'd have to go through extra steps to form that Wittig reagent, or doing some sort of nucleophilic attack and then doing an elimination there. So this is a pretty handy reaction. All right, questions on that one? The next reaction is similar. Let's see what this is. We have a Claisen reaction. Which is similar to an aldol, but it is with an ester. And usually the base for this reaction is NaOR. So it's whatever the R of the ester is. So if this was an ethoxy, you would use sodium ethoxy there. And the product we would get here is the original ester. We're going to draw a new bond from the alpha carbon, and then the carbonyl part of that. So if you think about it, this is the 1, 2 from that ester. 1, 2. This is the Claisen reaction or Claisen condensation. And it forms a beta keto ester. The beta part of it is, if this is the alpha, this is the beta, and you're making a keto group next to the beta ester. And then for the base, you want to use a matching alkoxide. So that is the Claisen condensation. It works very similar to the aldol, except now we have this carbonyl with the ester that gets kicked off as a leaving group. If you have a diester that is long enough, you can do an intramolecular reaction. And get a cyclic compound. Oh, I made a mistake on that one. Hang on just a second. Okay, my whiteout is not handy, so I'm just going to draw below here. My apologies. Okay, so that is maybe a little bit difficult to see that is green there. So this is your original ester from over here. And then I've just drawn it to the alpha carbon, and that's making a new bond to the carbonyl here. And if you count from just the alpha carbon, this is 1, 2, 3, 4, 5. So I know how big the ring is. The alpha carbon is going to attack carbon 5 or the carbonyl carbon and form this new bond here. The double bond is formed from kicking off of the ester. So if you have the cyclic structure, this is a Dieckmann reaction. You can also form cyclic reactions from aldehydes if it, again, is long enough and you have two carbonyls in the same molecule. All right, questions there? I need to add a new page, so I have to find page 15 in my book here. All right, this is still the carbon page. Okay, so if we have a ketone with that's unsymmetric or asymmetric, we add LDA minus 78 degrees, and you add to that an R prime, or whatever R group with an X here. This will add or form your enolate at the less substituted position. And then you're going to form a new bond to an R group here. So this is another way to add a carbon at the alpha carbonyl. This goes to the less substituted. So this was a methyl, this was some other group, had one R group on there. So our enolate will form here at the alpha carbon that's less substituted, and that enolate, once formed, can attack this R group and kick off the halogen or leaving group there. Questions there? All right, if you wanted to do that same reaction, except to the more substituted side, you use sodium hydride at room temperature, and then add your R prime X. So this is your thermodynamic versus kinetic control, just like we did with the dienes. We did one reaction cold, it resulted in different product than running the reaction warm. So in this case, we also want to use a different base. Lithium diisopropyl amide is a little bit more bulky also, and so it will grab the more available proton there. All right, questions there? Okay, the next one, we have two more to add today, is the malonic ester synthesis, which starts with this diester. And the pKa of that diester is, I think, was around 11 or 13, something like that. So what you would do with this is get a base. So you can use NaOET. You're going to add to that R prime X. Hydrolyze it with acid, and then heat it. So the first thing that will happen for steps 1 through 3 is you'll get an addition of the R group. So the base will form the enolate in between and attack the R prime. So you add the R prime. The acid, if you remember from last chapter, when we add acid to esters, that's going to form it to the carboxylic acid. And then when you heat it, one of those will be lost as CO2. Oops. So you have the diacid, and then we're going to lose one of those acids as CO2. This is the malonic ester synthesis. And the next one is a similar process, but it starts with a different starting material. We start with an acetic ester. We use NaOET. R prime X. And that same acid and heat. So you get your acetic part of it, or acetone. You find the alpha carbon, which is in between there. That's where our R group adds. And then the other stuff, this whole part of the acid here, or the ester, that will get hydrolyzed to the acid. And then when you heat it, it's lost as CO2. So that's a handy tool to have if you are needing to form some sort of ketone, and you have an acidic proton here. These ones are kind of hard to see if you're not looking for the acid or the ketone, but they're there for you to use it in your synthesis if you wanted to. All right, any questions on those? Okay, so you have a test coming up tomorrow, and I just wanted to remind you when you're doing your synthesis problems that in the back of your reaction books, you have an index of reactions. So let's say you were trying to make well, let's say an ester, and that's what your target molecule is, and you are starting from an acid anhydride. Now you know you can go to your chapter 21 functional group transformation page to find reactions that you can do that. Or if you're looking to make a ketone that is an alpha beta unsaturated ketone, that's the one we just added. That's chapter 22 in the carbon-carbon bond forming reaction page. So just remember that you have that index in the back there that will come in handy either for the exam. This is from part C of chapter 22. And the first one is dealing with, or all of these are dealing with, alpha beta unsaturated carbonyls. So this can be an aldehyde or a ketone. So this is the alpha beta unsaturated carbonyl, so that double bond there, which if you just had a regular carbonyl, you could make this using Br2 plus pyridine. We saw that in the functional group transformation page. So if you add a Grignard to this reaction, followed by a water or acid workup, you're going to add the Grignard to the carbonyl. So it's not going to do anything to the double bond there. It will just add the carbonyl. So we're going to get an alcohol, and the R double prime goes there. So this is considered a 1,2 addition. So you're adding it to the 2 position here where oxygen is 1. So a Grignard is going to add to the 2 position. You have the same alpha beta unsaturated carbonyl. And you add the Gilman reagent, which is that cuprate. Followed by acid. This will add to the 4 position. and that enol, or that double bond, goes away. So what happens is this R prime is going to attack at the 4 position, and then you get the double bond shifting here, and these electrons go on to the oxygen to form the enolate, and those electrons from the oxygen can come back down, and then the double bond electrons will pick up a hydrogen from the acid. So you have the single bond here, and the carbonyl stays intact, and we add an R prime or double prime group at the 4 position. So this is a way to add carbons. Now we have a way to add a carbon at the carbonyl position. We can add it at this position here, the alpha position, using LDA and some electrophile. And now we can also add it to this position here using a cuprate. All right, questions on any of those 2 reactions? So a Grignard is a weaker nucleophile, which will add to the 1,2. And the cuprate is a little bit stronger, and that will add to the 1,4 position. If you have a diketone, this is considered a Michael donor. We can first add a base such as potassium hydroxide, followed by an alpha beta unsaturated carbonyl. I'm putting a Q on the other side of that carbonyl there. We follow that up with acid. So that KOH is going to grab the proton in between here and make that the enolate, which can do a 1,4 attack at this position. So you form a new bond at the alpha carbon. And we have one, two, 3 carbons there. So I'm going to add 1, 2, 3. At the 3, I have the carbonyl. And then this is the Q. So this alpha beta unsaturated carbonyl here, these are Michael acceptors. So Q here can equal H. So it can be an aldehyde, a ketone, an ester, an amide. And those are all going to be on the other side of that alpha beta unsaturated carbonyl. You can also use this nitrile or something with the NO2 here. So any of those things are considered Michael acceptors. These do a Michael addition. And that results in a 1,5 dicarbonyl. So a 1,5 dicarbonyl. And the 1,5 is the 1, 2, 3, 4, and then the 5th carbon there. So we get our 1, 2, 3, 4, and then this 5th carbon. So Michael donor is between the 2 carbonyls, and then you add this alpha beta conjugated carbonyl, and that enolate that forms in between there is going to attack at the 4 position. And then we're adding this whole chain here. This is kind of the similar addition to the cuprate, where you get the loss of that double bond and your carbonyl stays intact. Questions on that one? And then, of course, there is an intramolecular version of this reaction, which is actually 2 things. That is the Robinson annulation. And that results from something like this. Where usually there is an alpha carbonyl here. So there wouldn't be a Q, it would be a carbon. You add sodium hydroxide and heat. And what you end up with is it's a Michael addition followed by a aldol condensation. So the enolate will form here. You get the addition of the 1,4, which is the Michael addition. And then after that, you get the enolate forming on this carbon, which can attack the other carbonyl to do the aldol condensation. And then another one that we should add here is the stork enamine synthesis. The stork enamine synthesis is if you want to do an alpha beta unsaturated addition at the 4 position, but this is not a Michael donor, it's not strong enough. So what you can do is add an amine, a diethylamine or secondary amine in the presence of acid. That will form the enamine, and then you add your alpha beta unsaturated carbonyl. So that can be the Q, followed by acid. Form your new bond at the alpha carbon. Oh, I had too many carbons. Should be this one. So the 1, 2, 3, and then this is Q here. So you'll still get the 1,5 dicarbonyl, but the big thing here is that you had to use that secondary amine in order to get there. So this is a stork enamine. And then if you want to draw the intermediate here, you can. So this is the thing that will be strong enough to attack at the 4 position versus just the enolate. All right, questions on any of those? So anytime you have this alpha carbon and there's only one carbonyl here and you want to do a 1,4 addition, you have to make it a better nucleophile by going through the secondary amine. And it can be any secondary amine. So you can have just methyls here, or it might be part of a cyclic system. And then you can do the 4 addition. If you didn't have the amine, you would not be able to add here. It would add to the carbonyl itself. All right, any questions there? So this is on your functional group transformation page, which should be 11 in your reaction book. And the first one we're going to start with is ammonia. And we're going to react that with an alkyl halide. And when you do that, the ammonia is going to attack the alkyl halide and add 1 R group. And then if you remember, every time you add an alkyl group to a nitrogen, that makes it more basic. So that's going to keep reacting until you've added as many R groups as you can add. So you're going to end up with this ammonium salt with the halogen as the counter ion. So ammonia plus an alkyl halide is going to alkylate as many times as possible. So if you wanted to make a primary amine, this would not be the way to do it because it won't react just one time. Instead, the way to make a primary amine, or one of the ways, is to use sodium azide. And then follow that with H2. So N3 is azide. And then we react that with H2, palladium, or you can use lithium aluminum hydride. So the R, or the N3, which is a minus, can form a new bond here. So you would get N3, and then you reduce that, that will form the NH2. So that is one way to make a primary amine. The next way is the Gabriel synthesis. And in this one, you actually start with thalidomide. So your nitrogen source is right there in that ring. And then what you do is take potassium hydroxide, which will remove the hydrogen from that nitrogen. And then you're going to add an alkyl halide so that N- can attack the R group. And it will only do that one time because we have 2 electron withdrawing groups on that nitrogen. So we won't get over alkylation. And then after you add the Rx to remove the rest of that stuff that you don't want, we'll add NH2, NH2. Then you have N, H from there. Pick up another hydrogen and our R group. This is the Gabriel synthesis. The next reaction involves, you can use this to make a primary, secondary, or tertiary amine. This uses an aldehyde or a ketone. And then you're going to use an amine. Can be primary, secondary, it could even be ammonia. And then in the same reaction, you're going to add sodium cyanoborohydride. So with this reaction, you're first going to form the imine, like you would normally with the ketone aldehyde plus an amine. So that'll form the imine, and in the same reaction, you'll also reduce it to the amine. So for this, you can use NH3, primary or secondary amine. we have R NH2. In this reaction, you add methyl halide in excess and follow it with silver oxide. And this will do a Hofmann elimination. So that gives you the least substituted alkene. Most of the eliminations that we've seen will give the most substituted. This one gives us the least. So the nitrogen is going to alkylate multiple times till it forms that quaternary amine or ammonium, and then that silver oxide will eliminate to give us the least substituted. Questions there? All right, so the next reaction, this is chapter 23 continued, involves a secondary amine. You add sodium nitrite with HCl, which forms this HONO, or they call it HONO. That will form a nitrosamine. Or an N-nitrosamine. And a lot of these derivatives are formed in situ, so in your body if you're exposed to primary or secondhand smoke, and that is dangerous for your DNA. So that can happen a lot of times when you're exposed to cigarette smoke. All right, so if you do the same reaction with a primary amine, we form the azide. And that azide is a very good leaving group because you're losing N2 or nitrogen. And most often we use these reactions on an aromatic ring. So if you have this aryl ozonium, you can react it with copper with an X here. Oops. And that will just replace the diazonium with whatever the X was. Where X can equal Br, I, Cl, Cn. So if you wanted to add a nitrile to the benzene ring, you can do that very easily. And then you can also use, instead of copper, X, HBF4, if you use that reagent, will allow us to fluorinate. So we didn't have a way before to add fluorine to the benzene ring, but now we do. If you just add water to that reaction, well, I don't know why you would want to do this, but if you added water, that will just add a hydrogen. So you'd get benzene. And then if you added, oops, I'm sorry, that would make it phenol. So that's a different way to make phenol there. And then if you add H3PO2, that will add a hydrogen. So in order to use this diazonium, you have to have aniline present, so the NH2. So it can't be the nitro group, but if you were going to do a synthesis, you would start it with the benzene, add the nitro group, reduce it to the amine, and then make the diazonium, followed by copper X. All right, the last reagent that we'll add to this for chapter 23 is using aniline. And if we try to do add Br, nitrogen is an ortho-para director because it's electron donating. But it's also very strong of an electron donator. So what you can do, or what happens, I guess, is you brominate ortho, ortho, and para. So it's going to add that bromine to all of those positions because it is so strongly electron donating, and that benzene ring gets very reactive. So for that bromine reaction, it'll brominate several times over. If you wanted to avoid that overbromination, or if you wanted to do a Friedel-Crafts reaction using aniline, you'd have to acetylate it. So react this with acetic anhydride and make that a C double bond O CH3 coming off of there. So we'll encounter some of those reactions later. Questions on any of these reactions?